Hello and welcome. In this video, we'll be looking at wheels, how they roll and slide. Let's get right into it and look at the wheel I'll be using to show the motion. Now, this is a skateboard wheel, which is not an ideal wheel by any means. It has a hole through the middle where the axle would go, and the middle of it has the bearing that you can see, which is not the same material as the wheel itself, and the wheel is a bit of an irregular shape, but it is more than good enough to show the motion. And then the ideal sort of problems that you will be looking at are very similar to what you'll see. And as you can see in the picture, it has a mass of 75 grams. And as you can see here, it has a diameter of 49 millimeters. So let's look at the first motion in tracker. So here's tracker, and I'll just let the motion play out first. And there it is. You can see I drew with a black marker, I drew a line on the wheel just so it's easier for me to track and so you can see with your eyes easily how the wheel is rolling. And as you can see, this motion is simply the wheel just rolling across the screen without any slipping. And you should intuitively see that there is no slippage. So let's go and look at the equation of motion for this. So as always, we start with a free body diagram of the situation we're looking at. And as you can see, we have a wheel represented by the circle with a radius of r and an angular velocity of omega and a linear velocity of v. And very simply, the one equation of motion for this is that v equals omega times r. And that is all there is to it. If we look at the next slide, here is from the tracker data, the mark angle, so the angle that the marking is at versus time. You can see the angle is constantly changing or linearly changing, and it's changing at a rate of 12.6 radians per second, which is the angular velocity of the wheel, 12.6 radians per second. So from that, knowing the radius of the wheel, which we know since we know the diameter of the wheel, you can quite easily calculate the linear velocity of the wheel. Now, I won't do that, but here we have the tracker data from that same video showing the linear velocity, and you can see here it shows it to be about 0.31 meters per second, which if you take a minute and calculate the velocity we would expect, it is decently close to what we would expect within a few percent error, which is expected when you do experiments like this. So now let's look at the other motion in tracker. And here we are again in tracker, and let's just let this second motion play out. And as you can see, in the first part of the motion, the wheel starts by sliding across the table, and then it gradually accelerates, or rather accelerates angularly, and starts to roll until it reaches the required angular velocity for it to match the linear velocity of the wheel, and for it to continue rolling with no further acceleration. So now let's go back to the slides and let's look at the equations of motion for this. So once again, we start with a free body diagram of the situation we're looking at. And you will notice that it's the same free body diagram from before. We just now have a force of friction that is going to be angularly accelerating the ball, or the wheel, sorry. So first off, we have the mass moment of inertia, or I, of the wheel, which is equal to 1/2 mass times the radius squared. Then we have the force of friction, which is equal to the coefficient of friction, of kinetic friction. Again, this is kinetic friction because, as you saw in the tracker video, the wheel is sliding across the ground, times the normal force. And in this case, the normal force is equal to gravitational force, which is equal to mass times gravity. So then we have that the angular acceleration alpha is equal to the force of friction times the radius of the ball, which is just the moment due to the force of friction divided by the mass moment of inertia. Now, plugging in these equations and simplifying gives us that alpha is equal to 2 times the coefficient of kinetic friction times gravity divided by the radius of the wheel. And you should try on your own and plug these in and simplify and see that this is what you get. Now, this is not the end of the story. There is another part to this, which is the fact that this force of friction is going to be decelerating or negatively accelerating the wheel. And that acceleration is going to be equal to the force of friction divided by mass. Now, I'm just assuming that in the force of friction itself, there is going to be a negative term. That's why I didn't put a negative out here, but you should appreciate that it's actually going to be decelerating the ball, not accelerating it. And then if we integrate that, we get that the velocity is equal to the force of friction times time divided by mass plus the initial velocity. Again, this first term, I'm assuming that the force of friction is negative. That's why there's no negative term in front of the whole term. Now, another thing I'd like you to appreciate is that this angular acceleration only exists when the wheel is sliding, and so does this acceleration here. And the wheel is only sliding when the velocity is greater than the omega times r that we looked at in the previous example. Well, it also exists when the omega times r is greater, but for this example, it only exists when the velocity is greater. So as soon as omega times r becomes equal to velocity, we go back to the previous example where the wheel is just rolling and there's no more acceleration, angular or linear. And I would just like to appreciate that. I also want to point out that if you ever saw planes landing, when they land, they hit the ground and there's a plume of smoke when any of the wheels touches the ground. This is exactly why, because the wheel has to slide across the ground and accelerate very fast in order to start actually rolling and not sliding. And when the wheel slides, the plane is going so fast that there's a plume of smoke that just blows up from the wheel. Now, here's the graph of the tracker data from the video we just looked at. And as you can see, unlike last time where the line, there was just a straight line, this time, you see it starts from a horizontal and slowly goes down into a straight line. This is where the ball is accelerating and starting to roll. It accelerates, and then starts to go, and then the angle is a straight line. That is where it reaches the angular velocity required for the velocity that the ball is going, and keeps going at that angular velocity. Likewise, if we look at the position of the wheel, you will see that it starts off with a larger slope, or a steeper slope, than here at the end, after it has decelerated and started going at a constant velocity. And that is everything I have for this video. I hope you learned something and that you will find it useful when you're solving problems with wheels in the future. All right, have a great day. Goodbye.